Hello everyone, welcome back. So, in the last class we saw that what are the aspects in which basically CFD can be really useful, and it can basically assist the experiments in a big way in terms of getting more data points, doing simulations where experiments are not feasible, or even in terms of cost and money, cost and time, and from the safety perspectives. Okay. So, today we are going to discuss about what are the steps that we need to follow when we are doing CFD. Okay. So, we have seen some applications, and you might be seeing some very beautiful pictures. If you go to internet and type CFD, you would see nice pictures. Okay. It may be some contours, some streamlines. Okay. So, then the question is like how do we get those kind of pictures, or how do we get those kind of images. So, they are of course, post processed, you have done some simulations and you are presenting in a way that it is understandable to the user, right. So, before we actually get to the picture, there are a lot of things which are involved in doing CFD. So, the first thing here is the preprocessor. Okay. So, you might have to there are various steps you have to follow before we get to those very nice images. Okay. So, first of all, we need to basically create a very nice CAD model. Okay. If you can get it, the CAD model, it can be different format. Okay. It can be step file format or any different format, and you have to basically get it and import it in your favorite grading software. You need to make sure that the geometry is closed. Okay. And it is watertight, okay, because if you have leaks, the flow might get inside. Okay. So, you have to basically separate the solid domain and the fluid domain. Okay. If you do not have the geometry, then you have to create a geometry. You might have the points, okay, the data points which can be used to create the geometry. Okay. And there also you need to make sure that you are basically ensuring that there are no discontinuity in the geometry if it is not desired. For example, if you are designing an aerofoil or a turbine blade, you do not want that there is a discontinuity in the shape, and that is triggering the flow to become transitional, okay, or turbulent, right. So, you do not desire all those things. So, the geometry creation is a very important step where you need to make sure that it follows the CT continuity on the surface, and it does not have any leak, okay, it is watertight and all those things. Okay. So, after you created the geometry, second thing is to create a mesh, right. So, before you go to the mesh, we have to basically define your computational domain. So, what is your computational domain? So, let us say if this is your flow past an aerofoil, okay. Sorry, I will make it better. Okay, let us say if there is a flow past an aerofoil. So, you can choose different kind of topology. Okay, you might want to create a domain which is like this, okay, where there is an inlet and there is an outlet. Okay, or you might want that, okay, I want to create a domain like this. Okay, that you can define your topology that you want. And in certain cases your topology is restricted by the requirement that you have. For example, let us say if you are simulating a cascade, okay, which is again a blade, but there are blades on top also and then blades on bottom also, right. And if you are simulating one single blade, then you have to ensure that you are simulating like this. Okay. So, in this case you cannot, you do not have the luxury to use a domain like this, because you need to take the effect of this blade to this blade and this blade to this blade, right, because it has got certain confinement. Okay. So, there are certain cases where you have to have the inlet and outlet. There are certain cases where you can basically define just a far field and do away with that. Okay. And then again this is for external flow, you can have the internal flow also. Okay. So, in the internal flow you have the external geometry given, and the inside is your computational domain. So, you have to discretize within the body, right. So, the flow can be external, flow can be internal. If the flow is external, then you have to basically find out what is the computational domain, so that you can apply your boundary conditions properly. If it is internal domain, then your domain is defined, you have to discretize and create a nice mesh there. Okay. You have to set up your material properties. Okay. For example, you can, for the solid you can use aluminum, or for the liquid or for the fluid you can have some ideal gas, okay, or air or nitrogen, whatever thing you want. But this is an step which can differ, you can define it on your solver also. Okay. And you can also define a bonding condition here, or you can also define in your solver. Okay. So, but what you are going to define, you need to basically take care of that during the grading stage. For example, if you are doing a periodic bonding condition, right. So, what is on top is on bottom also, right. So, a good approach would be like if you have, let us say 100 points here on here, then instead of 100 points here also, right. If you have let us say 50 points here, then you can have 50 points here also. So, that it will conform to each other. So, okay, so this is a conformal periodic system. Of course, if you do not have, you can still interpolate and do that, but if you have the information that okay, you are going to apply periodic bonding condition on top and bottom, okay, then you can accordingly define your grid points and accordingly decide your computational domain. Okay. So, in some softwares you might have to tell already okay, this is going to be periodic, and then it will accept it, that in the solver. But if you have your own solver that you have developed, then you can just take care of the topology that you want according to the bonding condition, make your grid and then take that grid, and in your solver you can define the bonding conditions the way you want. Okay. So, after you have done so, after you have done the pre-processing, the next step is your setting up the solver. Okay. So, the first thing that is what kind of equations that you are solving, okay, in your setup. Is it your incompressible or compressible, okay, because as you will see that your solution approach will vary whether you are solving a compressible flow or an incompressible flow. Okay. Okay, that is one thing. Secondly, is your code dimensional or non-dimensional, okay, because accordingly you have to give your bonding condition value, initial condition and so on and so forth, right. So, it can be non-dimensional or dimensional for each of those. Okay. So, all this information you need to set up in your solver. Okay. So, if it is incompressible, you might only do the mass conservation and momentum conservation, but if it is compressible, then you might need to do all mass conservation, momentum conservation and the energy conservation. Okay. The other thing is that whether it is a 2-dimensional flow or a 3-dimensional flow. Okay. So, if it is a 2-dimensional flow, the momentum equation will be only 2 x and y. If it is a 3-dimensional flow, you need to have all 3 momentum equation. You have certain solvers which are by default 3-dimensional. Okay. Let us say for example, if you are using open form, okay, so it has got a 3-dimensional solver, but you can still use that solver to solve a 2-dimensional problem. Okay. So, what you need to do is that in the third direction you can have certain number of grid points, very few minimal grid points, okay, because it is by default a 3-dimensional solver, but you can use symmetry conditions there to ensure that okay, those 3-dimensional boundaries are not affecting the flow on the 2D surface. Okay. So, accordingly you can set up your equation. Okay. We will see that if the flow is compressible, we need an additional equation which is equation of state. Okay. And why is that? Just a brief mention here. Okay. So, in the compressible flow, what are the variables that you have? Okay. So, the variables that we will have is rho, u, v, w, p and also temperature, right. So, these are the variables that we have for the compressible flow. Okay. But what are the equations that you have? You have mass conservation, that is 1, okay, this is mass, and how many momentum? You have 3 momentum x, y, z. Okay. This is, let us say we are doing a 3D problem. Okay. And then you have one energy equation. Okay, how many equations you have total? 3 plus 2, 5. Okay, how many variables you have? 1, 2, 3, 4, 5, 6. Got 6 variables. 6 variables, 5 equations. How do you solve it, right? So, this is an underdetermined system. So, in order to solve that, you need an extra equation, and thankfully, we have that equation, because we know that from thermodynamics is that our pressure and density are related to the temperature. Okay, and if your flow is ideal gas, then you have P equal to rho R T, right. So, you can, this is the equation of state that you need to set up, but if it is not ideal, you might have certain other equation of state that you might have to use. Okay. And of course, you can have other physical models. For example, how does your viscosity vary with the temperature, right? So, viscosity, what are there are models like Sutherland's law, okay, or there are power law. So, what is the model that you are using there? So, all these things you need to set up. If what is your gamma, whether it's the flow, the fluid that you are using is diatomic, monatomic, triatomic, and so on and so forth, right. Then after you set up the transport equation, the third thing that you need to decide is your physical model, okay, in the sense that what are the turbulence models that you are using. Okay. So, this is whether you are solving it through LES or RANS, your turbulence model will be different, right. If you are doing even within RANS, you will have different kind of turbulence models. The popular models are Spillart-Alamaras model, SA model, K epsilon model, K omega model, SST K omega model, okay, and there are a range of models. So, these are the turbulence models. Then you have now transitional models also, which basically cater to the transitional flows. So, you can have this 4 equation Mentor's SST model, okay, and then you can have this laminar kinetic energy model. So, all those different kind of physical models are present, that. So, you need to select depending on your flow what kind of model that you want. If you are using LES, then LES has also got different models. Okay, you have got Smagorinsky model, you have got Weyl model, you have Wall model LES, all those kind of things are there that you need to decide. If your flow has got combustion, then you have different models for combustion also, whether you want an ED dissipation model or laminar flamelet model. So, that model you have to decide. If you have a radiation, then you in the radiation also you have model that you need to choose, and if there are other processes, you have to choose those models as well. So, once you made your grade and chosen all those things, then the second thing is that what are the solver settings that you are going to do is basically first thing is initialization, how to initialize it, whether you want to initialize from the inlet, from the outlet, you want to put a hybrid condition. So, typically in a range simulation, it does not matter how you initialize it, because ultimately the steady state will be the same, okay. But this may not be true in a DNS or LES, because even a slight perturbation can change the things, okay. In RANS also, I mean, regardless of the initialization, you should get the same result, but it will definitely affect your flow timing, I mean simulation timing. So, if your initialization is proper, you might be able to get the converged result faster, and if this initialization is not according to how the solution should look in the end, then you will get the very slow convergence, and sometimes it may diverge also. So, initialization plays a big role in basically deciding the fate of the solution, okay. You have to have like solution control, like at what time you want to write the output file, what are the things that you want to see, the monitoring solution, like do you want to see the residue, okay, what are the residue that you want to see, whether it is density, velocity, energy, and all those kind of things, okay, and the convergence criteria, like when it will be converged. So, in the RANS simulation, you can say that okay, when it reaches to 10 power minus 5. So, when I say it reaches 10 power minus 5, what do I mean? It means that I am looking for a steady state solution. Let us, I am looking for a solution where density has got a certain value at a given point, right. and now if the change in that density between the previous iteration and the current iteration is less than 10 power minus 5, okay, then we would say that okay, solution has converged. So, that is the criteria that we can decide. Okay, I am just giving an example of density, but it can be any variable, it can be the turbulence quantity also, it can be k and epsilon also. Okay, so, that convergence criteria, that when do you say that solution is converged. Okay, please keep in mind discussion is for Ray's model only. Okay, if the flow is unsteady and if you are doing an LES or DNS, you will not see the residue going down to 10 power minus 5. Okay. So, in that you will have different criteria for assessing whether your simulation has got a meaningful solution or not. So, that we will discuss in the future classes. Okay. So, after you have done this, so this is all the solver part. After you have done the solution and it has converged to a certain level, okay, what you can do, you need to basically analyze your data set. Okay. So, basically you have at every grid point, so like the grid that we made earlier. So, for every grid point you have the value of the converged value of rho u v p, rho u v w p. Okay. From that you want to calculate certain values. You might want to see the velocity, you might want to see the change in pressure, temperature, density, etc. So, you can use your contours, okay, or you may be interested in finding let us say vorticity omega, okay, or you might be interested in finding the skin friction or the Nusselt number, the heat transfer and so on and so forth. So, you can calculate all this from these variables. You have the grid and you have these variables, you can calculate those gradients and plot it and see it, how does it look like. You can have the line plots, okay, let us say what is how the things are varying across this line, let us say at the center line, okay, then you can have a line plot, or if you want to see the 2-dimensional thing, you can make a contour. If you want to the 3-dimensional thing, you can make a isosurface, right. You can have velocity vector, how the velocity is changing, you can have streamlines, okay, you can plot all those different kind of things for your for understanding the results of your simulation. Okay, and as we have discussed that because we can refine the grid a lot in your CFD simulation, if your simulation quality is good, you should be able to get these gradient parameters also nicely. Okay. I will just take you through some of these examples of this pre-processing solver setup and monitoring solution to the post processing. Okay. So, for example, if I want to simulate this NASA trapezoidal wing and I have this CAD model. Okay. So, what I will do, I will just first get the CAD model. Okay. So, this is the CAD model I got, okay, from the same geometry. Okay. You can see that you have a slat here, okay, this is slat and this is a flap. So, both are present here also, there is slat, there is a flap and there is a wing. So, I have got an equivalent CAD model here. Okay. So, the geometry is available to me. Okay. What I need to do is now make a and this is just the view of the same thing. If you take a section there, so this is your 2D view, okay, at a given section. Okay. You can have a slat here and a flap here. Okay. And once done that, here I am saying that how to make a grid. Okay. On the same thing, you have to design the surface grid and then you have to design the volume grid. Okay. So, this is a multi-element aerofoil. Okay. So, you have to make sure that there is enough boundary layers on the body, okay, and then there are regions of high gradient, okay, very close to the body like here, and away from the wall you can use an unstructured mesh, right. So, this is so we got the CAD geometry. I am not showing the domain here, but domain is somewhere like very far away, let us say here, okay, and you have to set up the boundary conditions at the end of the domain. Okay. So, you got a grid, made a domain around it, got a geometry, made a domain around it, and then made a grid around it. And while making a grid, you ensure that wherever you are expecting high flow gradients, let us say in the boundary layer very close to the body, you have refined mesh, and when you went away from the body, you basically can use a coarser mesh, because the flow gradients are not that high in that location. Okay. And then you set up the solver. Okay. And here you can see the monitoring that I was talking about. You can monitor your mass or the density, energy, momentum, your turbulent quantity that you want. Here it is nu T, and we will discuss what is nu T in future classes. But you can see that okay, my solution, and let us say I am setting my convergence level to 10 power minus 4. So, this is my 10 power minus 4. Okay. So, when every component has reached below 10 power minus 4, I can say that okay, my solution is converged. Okay. That means the change in the aggregate change, or the sum of the changes of the energy, let us say in this case the red one here, between the previous iteration and the current iteration is less than 10 power minus 5. Okay. So, we say that okay, it has converged. Okay. So, the x momentum, y momentum and g momentum, they say you can see that they have converged below 10 power minus 4, right. So, this is the parameter that you can decide, like when we should be satisfied that okay, now I can say that my solution is converged. When you run the simulation, you would see many times you would not reach the desired convergence. There will be fluctuations in the flow, okay, which is not dying out. So, there are various reasons for that. Sometimes it is numerical and sometimes it is physical. Okay. When it is numerical, it means that maybe you have not made the grid properly. Okay. There may be elements with very high aspect ratio. Okay. The orthogonality is not satisfied. Okay. So, there are or your solver setup could have problems. Okay. You are using a scheme which is not suitable for that kind of problem. But there are physical reasons also why it is why it may not converge. Let us say if the solution got inherent in unsteadiness, that means that the solution is not a steady state, but you are using a steady state solver there, right. So, what you will see, it will keep on fluctuating. Okay. Typically, let us say you are trying to simulate flow over a wing at a very high angle of attack, right. So, when you do that, what will happen that the flow may separate at that angle of attack, okay, let us say near the stall angle. So, in that case, if you try to use a range simulation for that angle of attack, you might have this convergence issue, right. Your, let us say your CL and CD will probably can do like this. Okay. It will not, it will go up to certain level, up and down, and after that it will start doing like this. That means that flow has got some inherent unsteadiness, which cannot be captured by that steady state range simulation. If you want to really capture that kind of flow, you have to do U range, which is unsteady range, or approaches like unsteady approaches like LES and so on. Okay. So, this is very important to understand that what flow physics you are expecting from the problem. Otherwise, you cannot differentiate what is the numerics and what is the physics. Okay. So, this is one example with what I was telling that. So, these are different turbulence models for that same flow over the wing. So, this is one of my papers that you can read. I mean, these all the results I am showing is from one of my papers. So, this is your experimental data, the blue one is the experimental data, and you have results from different models, SST, K-epsilon-RT, and then you have SA model, right. So, of course, the solution, the simulation was performed long back, around 10 years back. Now, we have better tuning of the models. Okay. But what is important point to see here is that when the angle of attack is lower, all the models basically agree more or less with the experimental data up to this point. Okay. And after that you can see that the simulation data or the computational values of the CL is now started deviating from the experimental data. And what is very important to see here is that, for example, you want to see the stall angle. So, this is your stall angle, for example, in the experiments, right, it is stalling at 35 degree. In the turbulence model, you can see that, for example, this your K-epsilon-RT and SST that stalls at around 30 degree, and for SA it is stalling much earlier, around 20 degree, right. So, when the angle of attack has increased up to a certain value, the flow started experiencing separation, okay. And whether these models are able to capture the separation, that is the question, right. If they are not able to capture the separation, you will not get the correct value or correct flow picture from the simulation. Okay. So, those are the things that you need to be very careful and you should have certain understanding of the flow physics that you are going to simulate before you basically use a model or trust the model. And this is just a visualization that I was saying, that you can see some streamlines here, nice streamlines, and you can see some kind of separation here. Okay. And of course, when you perform this unsteady simulation, because at high angle of attack the flows tend to be unsteady and your results might improve. Okay. So, this is what is the crux of the CFD process: geometry creation, grid generation, solver setup, simulation, and then post processing. Okay. So, I went through all these processes, and whenever you do any CFD simulation, you also have to go through all these CFD processes. And we went through one example, but you can take any flow example, or when you read any paper, you would see they would show you a grid, computational domain, boundary condition, what is the convergence level that they are using, what is the turbulence model that they are using, and so on and so forth, and finally they will show you the simulation. Right. So, with that we will stop today, and in the next class we will start discussing about different solution approaches. You can have finite volume, finite difference, finite element, and so on and so forth, and we will also start discussing about the governing equations. Thank you very much.